We will begin our discussion with curve and curvature. The curvature is a number we assign to each point on a curve. The number can show how curved it is around that point. Here we see a curve, and the slider here can change how curved it is, without changing its length. Now we imagine John is walking on the curve, and we are watching him with bird's eye view. The arrow shows the direction he is looking at as he walks through. The direction changes. We can see more clearly the direction change if we translate the arrows to the circle above, and we put a second point to indicate the start and finished position. More curved means more angle changed. So we define the curvature to be this limit, angle changed over distance walked. We are taking a limit because curvature is a local property. The curve can be more curved at a certain point and be more straight at another point. Until now, we were using the tangent vector. But actually, we can do the same with normal vector. With a 90-degree rotation, what happens on the circle above and the circle below are exactly the same. Now we can understand why the curvature of a line is equal to 0, and the curvature of a circle is equal to 1 over its radius. It's because when we were walking on the line, there is no angle changed, so the limit will equal to 0. When we were walking on the circle, the length is equal to the radius multiply theta, so the limit will equal to 1 over radius. Now, what if our curve is parametrized? If our curve alpha t has a special property such that alpha prime t is always a unit length tangent vector, then we can continue our definition to have this equation. Because we recall from calculus, when theta is very small, the theta, the arc length, sine theta, the tangent theta, and this segment are all quite the same, and the length of this segment is here. So we know the limit will be the length of second derivative of alpha. And please notice the curvature is also equal to the limit of green arc length over the pink arc length, or the limit of purple arc length over the pink arc length. This will be used a lot in the following discussion. So, what kind of curve alpha t will have unit length tangent vector? Here is an example. You can choose any point on the curve to be alpha 0, but the distance between alpha 0 and alpha 1 should be equal to 1. The distance between alpha 0 and alpha 2 should be equal to 2, etc., etc. That means if we still consider t as time, at time t, we had walked distance t for all t. Just like a robot is walking on the curve with unit constant speed. This kind of parametrization is called arc length parametrization. Two little notes for curvature. Notice that we introduce curvature before parametrization, because as soon as a curve is drawn, the curvature is there. The curvature is independent of what kind of parametrization we are using on that curve. And second, we indeed have a formula for any general curve, but it's a little more complicated. Now we introduce the surface. The surface is a function. It takes in two variables, and the output is a vector in 3 dimensions. We also require this function's differential to be 1-to-1. That means the x sub u and x sub v should be linearly independent, and they are not equal to 0. Because we need them to calculate a lot of things later. And the tangent plane is this plane, the plane tangent to the point P on the surface S. And we will consider it as a linear space in the 3-dimensional world. So we can do some linear algebra on this tangent plane. To calculate the area, angle, and length on the surface, we define first fundamental form on the tangent plane. It's a quadratic form. It takes in a vector on the tangent plane, and the output is the vector in the product with itself. If we choose a basis, x sub u and x sub v, we can determine its coefficient. If you don't like the quadratic definition, you can take the definition from here. The point is, we define 3 functions, capital E, F, G, and it's defined as the inner product of the x sub u and x sub v. Let's see how here EFG help us calculate area and angle. Here we have 2 points P and Q. The little distance between them is delta U, and the vertical one is delta V. When the points move in this direction, the point on the surface move in this direction by this much. So the little area, delta U and delta V, becomes this yellow area. When we look from above, this is delta U and delta V, and it becomes this area on the right hand side here. If we use the equation here, then we can have the area is equal to this integral. And the angle, we can calculate the inner product, and is equal to this one. First, we have alpha t, a parametrized plane curve. Then we put it in x to have our curve on the surface. A little change in t makes little change in u and v. On the graph, it's here and here. And little change in u and v makes point P move on the surface by this much. So for the final movement, we calculate the length of this green vector. Then we have this equation. When t moves, we integrate it over the range we want. Here we have an example. Let's calculate the surface area of torus. First, we have the parametrization, and notice that the range of u and v doesn't include 0 and 2 pi. So technically, there are two gaps on the torus. And then we calculate its first fundamental form. And we integrate it over this area. So this area doesn't include the black part around the square. And the width of this black part is epsilon. Finally, we let epsilon go to 0. Then we can know the surface area of torus. Normal vector. It's the unit vector perpendicular to the tangent plane. And it's also quite easy to calculate using this formula. And if we have different parametrization, the x sub u and x sub v might change, but the normal vector will stay the same. It's the most unique and important vector. Gauss map. If we translate all the normal vector to origin, then we have the Gauss map, a map from a surface S to a unit sphere. Now, the point can move in the two-dimensional surface. Let's start in one direction at a time. Normal curvature is the curvature we assign to a given direction. As you can see on the right, there are many curves that go through the point P and that have the same tangent line. They pass P in the same direction. They are all on the surface, but each curve has its own curvature at P. Let's assume they are all arc length parametrized. We draw the second derivative on the screen. And surprisingly, from this angle, the endpoint of those vectors are all on the same line. That means if we denote the angle between the normal vector and the normal vector as theta, the curvature multiplied the cosine theta will all be the same, and we define this number as the normal curvature in the direction. Given a direction, besides using a curve on the surface to define normal curvature, we can also observe how the normal vector change when we are moving in that direction. So this is where the shape operator dn comes in. dn is the differential of Gauss map, and the input is a vector in tangent plane. It is the velocity we are going to pass through the point P. Given the vector, this pink vector, we can choose a curve accordingly. It's this pink curve on the surface. So now we can travel on the curve. Our main point is this pink point, and now we can travel on the curve. The green vector is the normal vector, and the output of the dn will be the velocity of this endpoint. And we can translate it to the origin to see more clearly. So we have this point, purple point, here. Because the normal vector is a unit vector, the velocity of this purple point is perpendicular to it. So we can say that the output is also a vector on tangent plane, and it's this purple vector. And of course, the faster we pass P, the faster this point moves. We can look at it from another angle. The point is passing the point P, and we focus on this purple point, and we can see that it's indeed moving in the direction of this purple vector. Let's have another one. The pink point is moving in this direction, and the purple point is moving in the opposite direction. And if the surface is more flat, and the velocity of this purple point will be smaller. So let's summarize and add a little bit information of dn. It's a differential of Gauss map. It's a self-adjoint linear map on tangent plane, because we have already seen the input and the output, they are all on the tangent plane. And we will now prove the self-adjoint linear part in this video. And because it's self-adjoint, there exist two eigenvectors and two eigenvalues. Here is two eigenvectors and two eigenvalues. It's minus k1 and minus k2. That means the output is parallel to the input. And these two eigenvectors will be perpendicular to each other. So here, this is an eigenvector here, and we can see in this direction. The second eigenvalue and eigenvector. And a very important point is that the k1, k2 is the normal curvature in E1, E2's direction. The answer of this is in here and here. But normally, putting a unit vector in Dn, the length of the output won't equal the normal curvature in that direction, because this thing might happen. The output is perpendicular to the input, and this type of movement has nothing to do with the normal curvature we want. On the contrary, in the E1, E2's direction, all the output is in an effective direction, so we can have our beautiful result, and we call them the principal curvature and principal directions. Gauss curvature is the most natural generalization of a curve's curvature. Please recall that at the beginning of this video, we defined the curvature as the angle over the length, but it is also equal to the length over the length. So now we define the curvature of the point to be the ratio of two areas. and taking the limit where the pink area shrinks to 0. Now let's further assume our area is this rectangle-like area, and this is the principal direction. Then when the area shrinks to 0, it becomes this ratio, and the ratio of width and height becomes k1 multiplied k2. This explanation is very, very informal, but I think it gives us a good sense, a good feeling of what really happens here. So when the normal curvature is bigger, this length will be longer. Same thing happened here. Before we end our video, let's have a little more serious explanation. Here, the delta U and delta V change. So the ratio of areas equals this one. But from train rule, we know these two equations exist. So the Gauss curvature equals the determinant of shape operator, and this equal k1 multiplied k2 because they are the eigenvalues. Conclusion: Gauss curvature is very important, and there are so many amazing facts about it, but we don't have time to talk about them. So hope you can check it out when you have time, and hope you have a nice day too. Bye bye.